discussing a PhD thesis, Learning in the Quantum Universe by Hsin-Yuan Huang. He also calls himself Robert Huang, so I'm going to call him Robert from now on, just for simplicity. I saw a presentation that he gave at Stanford this week. I was inspired. I read his PhD thesis partially, and just as a side note, I worked a lot with Grok 3 actually on this one, and it's really, really amazing how helpful these agents can be, particularly in cases like this when you read a thesis, a scientific thesis that has a lot of important concepts that can be clarified through using an assistant. So that's just a side note, I think, for anybody who's interested in doing work like this, where you sometimes read technical papers that are not in your field. I think using either Grok 3 or GPT, the latest version, is certainly a huge help. So why am I picking this thesis? Why is it worth an episode? Well, we've been working on quantum computing for a while, actually, about 8 years now that we started working on this in this field. We haven't invested in it, but it is an interesting tangential field to our AI investments because it's about compute, it's about machine learning, it's about what actually can be done with compute. So a lot of questions that come up in the quantum universe actually help us understand the classical universe. So that's part of the payoff. And then, of course, hopefully at some point, eventually, we'll be able to make money with real investments in this field. It's a bit early now, and we haven't really done much investing. Also, recently, there's been a surge in quantum stocks like Rigetti, Quantum, there's a couple of other companies. We haven't participated in this because we believe that their financials, fundamentals, and even their technology is not ready for prime time. So that's our view on this. This episode is not about investing in the quantum space, though. It's really, we want to discuss Huang's PhD thesis because, again, it's for a couple of reasons. One is it's an important thesis for the field. I think it also is a nice example of how we think science should be done. So shout out to Huang, shout out to Preskel, his advisor, shout out to Caltech. You know, we've been critical of universities recently. Just the episode before this one, we actually spoke about the necessity to cut funding for universities for various reasons. Now, this is an example of how science should be done. It's an example of the validity of science and all of these things. And I just want to reiterate our view that we're certainly not against science by any means. Our fund, our whole livelihood is based on science and the translation of science from concept to technology and entrepreneurship. What we're against is the involvement of government in science and sort of the trust fund mentality of a lot of scientists. Now, this thesis is a perfect example of how it can be done, that it's the exact opposite. This is very useful. Huang has applied his theory to actual practical problems. He's worked with Google AI, so he's worked in the real world. So this is a perfect example of how science should be done. Now let's talk about the actual PhD thesis. The preliminary is this. What Huang does is three things. First, he shows that there are ways to classify quantum information and then use classical machine learning to predict the evolution of quantum systems. So that's number one, and that's huge because that means that we can extract information in a quantum way. So we can extract certain information that is quantum, and then we can train a model based on classical computers. So on classical computers, we can train a model. We can build a model that acts as if it was quantum, but it's trainable in a classical way. So it doesn't have this crazy exponential, exponential. So it doesn't go exponential on you right away. And you can still make good predictions. For example, you can predict entanglement entropy. You can predict how entangled the system is. So that's the first thing. The second thing that they establish in this thesis is that there are certain problems that don't give you quantum advantage. So not everything is about quantum computers. Certain problems can be solved in a classical way, even though they're quantum. For example, the average entanglement of a system can be solved with classical computers, and they've proven mathematically that that's the case. So I haven't gone into the proofs, I haven't done the actual math, and the purpose of this podcast certainly not to give a scientific critique of the actual thesis. The purpose of this podcast is to give people a sense of what it feels like to run a hedge fund. So you might ask yourself, why are we even talking about quantum systems? Again, I hope the beginning of this episode has made it clear that we are interested in investing in this space and understanding when pivotal science is done, then that's really important, because we could see a transition from this to technology and entrepreneurship. So the third thing that Huang is establishing, though, is that there are certain things that have a quantum advantage. For example, Pauli observables. We're going to talk about them. This is not even on podcast. It's March 8, 2025. This is Crim Delco. For the year, we're down 35.2%. The market is down 1.8%. We're underperforming by 33.4%. Before I go into the discussion, just a quick update on the market situation and the massive drawdown that we're suffering. It is driven by the market and by Tesla, by both. What I mean by that is that it's not just the market, and you can see that, of course, also in the massive underperformance that we have in the 30s. And that's because Tesla is suffering from a sales decline and a political backlash because Elon Musk is involved in Doge, and also a general political backlash internationally, particularly in Western Europe, against the Trump administration, and that is being manifested also in boycotting, for example, Tesla cars. Now, we're going to discuss this relatively briefly because I want to actually focus on Huang's thesis, but as this Not Even on Podcast series goes, we're still part of a general general purpose-driven mission here, which is to give people a sense for what it feels like to run a hedge fund. Sometimes we talk about science, sometimes we talk about positions, sometimes we talk about the markets. In this episode, I'm going to just mix it up because we had a massive drawdown, so it's, I think, important to update listeners on what's going on. And the drawdown in Tesla, because of the sales decline, is probably the least concern we have because that is driven mainly by the Model Y transition. And we're going to see massive sales increase when Model Y goes at scale, the new Model Y, which is a great car. And the Osborne effect is kicking in. And I think the markets are overreacting here, in my opinion. The other problem, though, the backlash against Tesla, that's a more serious problem. It's hard to say how this is going to manifest itself. Now, we believe that in terms of numbers, it's not so bad, meaning the extremists who are blocking Tesla stores or even shooting at Tesla stores, like in Oregon, they are in a very small minority, and there's enough people that will still buy a Tesla and maybe actually are incentivized now to buy a Tesla because they do agree with the policies, if they even are politically driven. We fundamentally believe that buying products and services actually is not politically driven. It's mostly utility driven. And I can give an example. For example, I have been always boycotting anything that Mark Zuckerberg is doing because I don't like the guy. But the point is also, I really don't need any of his products. I don't need Facebook. I don't need Instagram. None of that stuff. If I needed it, for example, I'm not a big fan of Jeff Bezos either, but I need Amazon. So it gives me utility, and that's it. I'm not in favor of Netflix because the Netflix founder wife is one of those private equity housewives that is funding inner city mental stuff and basically promoting homelessness in California and things like that. So I'm not okay with these things, but I still use Netflix because it gives me utility. So my point is, if something gives utility, and that's the main premise of our fund, invest in fundamentally new concepts, engineering practices with large impact. So if something can give you better value for less money, you will buy it no matter who is behind it, and that's our main thesis. So we're not too concerned about this. Now, the concern about the third and last thing, which is sort of the backlash politically internationally, that's a little bit more serious because there you have things like sanctions and all of that. But and then you have also an orchestrated backlash in Germany against Tesla, which is driven by the fact that in Germany most cars are bought by corporates and not by individuals. So when corporates buy cars, it's a bit like health insurance here in the US. so they can collectively decide not to buy Teslas to protect the car industry. So that's a bit of a problem. So basically, the way we work here at Orange Capital Partners, as far as Tesla is concerned, we're modeling Europe as being sort of like a Starbucks. It has Europe. It's a not growing small market. It's still good. It generates cash, but Europe is not going to be the big driver here. However, the European factory in Berlin can still be used for the Middle East and Africa and things like that. So that's fine. We think China and the US will be the growth drivers. And of course, there's all these other catalysts that come this year: the robotaxi, the unsupervised FSD, the semi, the Model Q, and Megapack, just to mention some of the most important ones. And then Optimus will be a bit later. We're incredibly bullish on these things. So that's the situation. But the drawdown is, to some extent, also an answer to the massive uptick that the stock had in the end of last year. So there's a bit of a correction. We're right now still higher than after the election. And we believe that there's certainly some more downside. We at Orange Capital Partners are mainly laser focused on our leverage. That's the key problem when you are exposed to situations like this. And that's what we need to monitor more carefully. So let's talk about this thesis now. Again, the thesis, learning in the quantum universe, important for several reasons. I think one is it asks some very interesting questions that related to quantum compute, machine learning, and the theory of computation, because it kind of asks the fundamental question of, if we have certain information which is quantum, for example, we take a molecule and we extract certain parts of information of that molecule. Like when I say quantum, I mean, let's say its spin, its energy, its Hamiltonian, things like that, which are quantum. We can then create a model. So with this atom or the electron or whatever particle we're looking at, we can create a model using some mathematical tricks that are described in the thesis, unitary T transformations. So think of it this way: we can take an atom and transform it and see what happens in a sort of random controlled way. Think of it like we're spraying salt on something, so it's controlled, but the way the salt corns actually fall on the food are still random. So we can transform that model and then extract information. So do a machine learning model, a classical machine learning model. So we have initial state, and then we have an end state, and we do this iterate, hundreds and millions of times, and then we extract knowledge from that. With that knowledge, with that model, we're able to predict quantum states and quantum dynamics of systems with classical machine learning methods. And, this is very Pascal-esque. They use a word for that. It's called the classical shadow. So we can have a quantum system evolving, and we can predict its quantum properties, some of them, not all of them, with classical machine learning. This is, I think, the key insight in the first part of the thesis. Really fundamental, in my opinion. Because what this means is that for certain things, like, for example, the evolution of the energy states, or the entanglement entropy of the system, or certain correlations between the particles, can be predicted with classical methods. And Huang has actually used his mathematical tools that he's applied here and experimented with it in Innsbruck in particular, big experimental group there, and shown that they can actually, so they took a system, they actually evolved it, a real quantum system, and they were able to predict its end state before it actually happened. So they were able to predict it. Now let me recap what they did here. They take quantum particles, they then transform them with certain mathematical tools, unitary T transformations, and you can, from that transformation, learn the evolution of the system, take the parameters, the weights that you learned from that model, and then use other systems and predict how they will evolve, and you can experimentally test that. So this is, I think, the bulk, in my opinion, the most important thing. So this starts getting interesting because now you have a couple of things. First, you have mathematical tools now to classify what entanglement is, what the evolution of entanglement is. You can do a lot of things now with quantum systems using classical machine learning. This is important for, let's say, a company like NVIDIA, of course, because now we're talking about using the old school, classical machine learning methods, Blackwell, GPUs, all of that, for quantum systems. Now, this is what the PhD is supposed to be, right? It's a fork in the road. It's starting a new, in my opinion, this starts a new science, which is a quantum compute information machine learning science. I'm sure Bresco will come up with a much better word for that. So again, I can't emphasize enough how important this is. And not surprisingly, when I went to the seminar at Stanford this week, I mean, the room was full, and I realized there's something special going on here. It's one of those. I've attended hundreds of seminars at Stanford in the last 2 years. This was one of those where I sensed the energy in the room. So, and again, kudos also to Stanford to have this kind of platform and invite people to such interesting seminars. So that's the first thing that he did. The second thing that I want to mention is that he also proved fundamentally that certain problems don't give quantum advantage. And those, in my opinion, are mainly the kinds of problems where you average stuff out. So for example, if you want to know how the quantum entropy evolves in a system, meaning if something is entangled in state T0 and then you evolve it to state T10, you can kind of predict, using these methods that Huang developed in the first part, to how the quantum system will evolve and how the average entanglement will be, or maybe what the minimum amount of entanglement will be, or the maximum, like things like that, upper bound, lower bound. Those kind of things, they don't give you quantum advantage. And I believe, I haven't read all the details, but I also worked with Grok 3 on this, by the way, so the system helped me quite a bit understand all the concepts. And what we concluded is that the reason there's no quantum advantage is because we're averaging out. So as soon as we average out, the quantum advantage goes away, because the quantum advantage comes, and this is the third part, when we talk about something like Pauli observables. So if we want to predict, if we have a system in T0 with certain spins, and we want to predict how the spins will look in T10, so after 10 iterations, how the system's spins will look. Well, then we need quantum computers to do that, because of quantum sensors, because we need to be able to evolve the quantum system in a quantum way, and we need to actually be able to capture each particle's quantum observables individually. And when that happens, we are in exponential O, so we need, we just don't have classical tools to outperform the quantum tools. So to summarize my takes from this PhD thesis, again, the three big takes is, number one, there are ways to train classically how a quantum system evolves and predict quantum properties of the quantum system with classical machine learning. Number two, there are certain problems where quantum computers and quantum sensors don't give you an advantage. Those are typically the types of problems where you predict average quantum states. And then third, there are certain types of problems where there is a quantum advantage. Those are the kinds of systems like Pauli observables, like the spin, for example, the spin direction in X, Y, and Z axis, when you have to predict how the system's spin in the x-axis will be going, let's say, from T0 to T10, and you want to predict precise Pauli observables, like, again, say the spin on the x, y, or z axis. Those are the types of things where you don't have, you need quantum sensors or quantum computers to actually predict, to predict or to deal with the quantum system in a learning way. So if you want to learn about the system, you need quantum computers, you need quantum sensors. So the conclusion of Huang's thesis is that there are certain things that certain problems we can apply classical machine learning to solve quantum problems too, and then there are certain problems where we need quantum sensors and quantum computers to evolve the system and solve those problems. And I think those are really important milestones for the science. Those are important milestones for quantum information theory, for quantum computing theory. So I think this is one of those theses where lots and lots of folks are opening up now. And I think one of the most interesting fields, in my opinion, if I was a young student right now, I would actually study math and physics and focus on quantum computation. This is what David Deutsch is doing. And I think that's a really interesting sort of cross-fertilized field because it helps you understand computation, it helps you understand quantum physics. So in other words, through computation, you learn about nature, and through nature, you learn about computation, which brings me to David Deutsch's fundamental thesis that everything starts with physics. So it's bits from it, bit from it. That's a whole different episode. But I think this is fundamental. Again, this is really fundamental, and kudos to this thesis. Like I said in the beginning, I think it's beautiful to see how science can have impact. This is one of those PhD theses that will have lots of impact. I am certain about that. And it also encourages us to keep working on the quantum computing space. There are things that can be done. Maybe some of the first wave of companies haven't been able to solve interesting problems. The commercial space hasn't picked up. But I think this is one of those areas. We're going to have to keep working on this. We're going to have to just keep digging, but this is opening forks, and this is opening trajectories that I think could be really, really promising for the commercial use of quantum computing and quantum sensors. Thank you.